So let me start. So the title is Towards Modeling of Classical and Quantum Mind in Superconductor. So it is quite old idea. It's from 2017, at least from my side. And as you will see later, this is very much interconnected into idea of current quantum computers, because we have in Wrocław, in Poland, quite recently, it was implemented new IQM computer that was doing quantum computations, but it has a very small chip. And also at the same time, we have this conference in Łódź in Poland. It was a hypercomplex seminar. Professor Yoshikawa was invited to Poland. He was participating in that, and then simply saying, he gave a great talk on classical superconducting computers. So I will try to cover this topic in greater detail. So the topic will try to interconnect classical superconducting computer with quantum superconducting computer, and there is a certain interface and certain possibilities. And in this framework, it's possible to have implementation of classical quantum mind in superconductor, because basically we have superconducting neural networks, and that are very low power consuming, that can reproduce human brain network. And also we can interconnect with small quantum chips, so we can test the existence of hybrid classical quantum mind. That's how it is. Okay, moving on. So first I want to point out what is the spiking neural network, and then I want to point out the rapid single quantum flux electronics, which is about pushing fluxon. And then I would like to give some remark on superconducting qubits and quantum annealing. And then I would like to point out about variational approach in designing new circuits. So basically this is perceptron, and perceptron is something that you know from information processing course, or it's just weighting of information that is placed at the input, and then there's summation, so there are some weights, and then the output is transmitted with some nonlinear function. So this is quite standard construction of neural network, classical neural network. And this is well-known perceptron, and you can basically implement continuous logic, non-sharp logic, fuzzy logic with that. And this is known from 60s. And this is how this artificial neural network works. So essentially it has some activation functions, and we have different type of nonlinear functions that you can use. You can have a sigmoid shape triangle and so on. So it's up to you to choose. And also this, if you think about Josephson junctions, they will impose certain type of nonlinearity ahead. Okay, so basically in a spiking neural network in biology, we have quite complicated situation, which is not exactly the same as with artificial neural networks that we are going to create. Well, I would say the type of neural network that function in a human brain is a little bit different from that one which we used to have in artificial intelligence systems. This is basically, we have spiking neural networks, in our brain, they have a feature of producing spikes very sporadically, not so often, and they have extremely low power consumption. And but we are also able to reproduce this spiking neural networks in artificial systems. So that's how it is. And basic model of spiking neural network known in our human brain is Hodgkin-Huxley model. And then we have this set of four coupled nonlinear differential equations. So this is, in a sense, art of solving those equations. Gives you the ability to model the spikes. So what you have here this concentrations N, M, H, and this is highly nonlinear system, as you can see. So here is we have N, M, H are dimensionless quantities between 0 and 1. And they are associated with potassium channel activation, sodium channel activation, and sodium channel inactivation, respectively. And the rest is about the certain type of coefficients that we are not going to go into detail. It's just a brief view inside. So basically, so in simplified version, the spiking neural network, so this model, which you have seen before, was kind of biological referred model. And some people have created the model, which is highly reduced in complexity, but still has this feature of behavior, at least main part of features. So you see this type of coupled of equations of first order, v prime, and this is v squared, 5 times v plus 100 minus u plus I, and I is some threshold, which you set, and then u prime is a times bv minus u. So those equations are codependent. So actually, you can place one equation to another equation, but anyway, in any case, it's like that. And then there is if voltage exceeds 30 millivolts, this is in our brain, by the way, then V is reset to C. So C is assigned to V, and then U is assigned value U plus D. And this is how it works. And then you can regulate its certain current I externally. So you can trace various types of dynamics with this neural network. And then you have regular spiking, then intrinsically bursting, then you have chattering and fast spiking. And it's up to you. It's a kind of numerical exercise. You can trace dynamics of this neural network with time. And basically, you have fast spiking, low threshold spiking, and so on. So this is like very much similar, but not the same model to biological model in our brain. But it's also remarkable to notice that it's 30 millivolts. If you deal with D-wave superconductors, high temperature superconductors, you have also 30. Usually, in case of low temperature superconductors, what you have is 1 volt, millivolt is able to break superconducting gap. But in case of high TC materials, this 30 millivolts sometimes is achievable. So in that sense, even with respect to signal strength, it's a bit similar, but not the same with superconductors, at least referring to superconducting technology. Okay. Then, then you have this basic features of superconductor, which you already know, and this is about this Meissner effect and this repulsion of magnetic field from interior of superconductor. So you can have superconducting ball or superconducting cylinder. You place external magnetic field and then you investigate how this external magnetic field is likely to push out field from outside. So there's induction of screen currents. So you can see how what's the situation with magnetic field penetration. So basically, all superconductors have this feature is that when there is external magnetic field that tries to penetrate the superconductor is inducing opposite currents. So this opposite current counteracts this initiated the current. So initiating magnetic field. So basically, ground state of superconductor is going to defend itself. Okay, and then there is definition of Josephson effect. So Josephson effect is a system of two superconductors that are likely to be narrowed. So there is a physical factor that modulates the intensity of superconductivity. So there is some sort of tunneling of Cooper pairs from one superconductor to another superconductor. By the way, this situation would be very much similar if we have superconducting grains in vacuum. If they come close, there is some microscopic wave function that from one object is touching another object. So there's two microscopic wave functions that are kind of interacting. So, and then you know already from the previous cases, at least specified previously, then you can have a tunneling Josephson junction as specified on the right side, or you can have a weak link as given below. So then there is dramatic difference of current voltage characteristics. And we are able to describe those differences in the framework of RCSJ model or in the framework of Ginzburg-Landau theory. And then we have well-known RCSJ model that stands for resistively and capacitively shunted Josephson junction. So this is that we have this. You have three components of. You have three components of current. One current component goes via resistor, one goes via capacitance, and one goes via Josephson junction. And now we arrive to the model of the spiking neural network. I'm just trying to give you a scheme. I don't think you can reach full understanding of this process just by one glance of your eyes on the screen. You need much longer than that, but basically you have here ideal superconductance that stands for those inductive elements. It's just part of superconducting strip, and then this superconducting strip is interrupted by non-superconducting material that stands for Josephson junction, that's a cross. And then you have also some resistor presence and capacitance presence. I think quite naturally, its capacitance is also associated with Josephson junction existence, because simply saying this, there is insulation material in between that does represent capacitance in great extent. Okay, so this is basically the scheme of the circuit, and then what you have here is system of two coupled differential equations that describe this phase difference between phi and phi c. So you have two types of phase difference, and this phase difference is nothing else as imprint of vector potential, in a sense, or is due to magnetic field. So here it's so you have two like Josephson currents, and then there is this coupling term, which is over here. All right. And then there is Josephson junction neural waveform with time. So maybe I supposed to magnify it a little bit. So there's flux, there are two flux, the flux and time. So you have flux, magnetic flux arise with time. That's how it's presented here. And then we have voltage increase with time. This is the way it's presented here. So yeah, so this is how it works. And well, we need to settle up some meetings. So basically we can solve those equations step by step. Okay, and now before going into greater detail, I want to first concentrate a little bit on idea of superconducting vortex. So what is a superconducting vortex? You have this two-dimensional superconducting strip, and you place in that superconductor inside system that generates magnetic field. So inside magnetic field of certain strength, like inside big coil, for example, or solenoid in a way. So what happens is that locally, in case of superconductor of second type, magnetic field is punching superconductors locally. So what happens here is that you have density of Cooper pairs. This is NS. And so it's like density of superconducting order parameter. And this suddenly decreased to zero. And then it's recovered. So it means that locally, magnetic field has killed superconductivity. So in a sense, superconducting order parameter was reduced to zero. And this is inside core of vortex. So vortex is a local punch of magnetic field via superconductor. And then in the place of magnetic field penetration, magnetic field intensity increases to maximum. It has a kind of shape like that. And also at the same time, there is a circulation of electric current, non-dissipative current, that there is no heat around vortex core. So in a sense, this flow of current supports magnetic field that is penetrated. And actually it turns out that this magnitude of magnetic field is not accidental. It's associated with integer values of magnetic flux. So you have multiplicity of magnetic flux that penetrates superconductor locally. And due to that, so there is existence of quantized vortices. In a sense, they have quantized magnetic field strength is not accidental. And actually, number of vortices present in given area of space is integer, is a multiplicity. This is a topological number. So you cannot have half vortex. You can have one vortex, two vortex, three vortices, and so on. So this is like topologically protected number. And this was actually the discovery of Abrikosov. So it was discovery of Abrikosov. This existence of vortices there was a Nobel Prize given. And actually, so there was a Ginzburg-Landau theory, and yes, and there was a solution of Abrikosov. And so basically, vortices can exist in the bulk of superconductor or in Josephson junction. So there are two types of vortices. Bulk, so you have uniform material. Let's say you can have thin or thick superconductor. And then you have this possibility of having vortices inside Josephson junction. So there will be circulated current across Josephson junction. Usually, magnetic field necessary to induce vortices in Josephson junction is much smaller. Is much smaller, and magnetic field necessary to induce vortices in bulk is much higher. Actually, turns out to be this value of strength of magnetic field depends on the strength of superconducting order parameter. So basically, this is function of temperature, and the closer superconductor is to critical temperature, the bigger is the size of vortex. So because it's like, you know, and the less is energy necessary to create a vortex. So basically, close to critical temperature, you have infinite number of vortices, or you can have something like that, very big number of vortices. And then it's a very good exercise to solve this problem of vortex with, you can think about that with, in the framework of Ginzburg-Landau theory, or in the framework of Bogomolov-Dejean theory, or you can even try to parameterize it, the vortex existence, by two-dimensional or three-dimensional RCSJ model. By the way, in one of my Master of Science theses, I had two defended. I have described the idea of closed vortices. So in a sense that vortex was like the whole interior was present, closed vortex of magnetic field was present in superconductor. And also in superfluids, you have vortice, so here's quantized magnetic flux, it's quantized angular momentum, it's a movement of mass in superfluid fluids. I'm not going to touch this topic. I just mentioned to you that there is a big big topic on that. I'm sorry for a second. Uh, so I have this. Okay, I'm sorry for a second. So basically, this. Yeah. So let me. So we have this vortex, and then we can also analyze situation of vortex presence in various superconducting and superconducting structures, and that's how it is. So now let us move to the topic of this rapid single quantum flux electronics. So this is how. What is the concept? Let's say you have a superconducting ring, and then you put two metallic electrodes, and then you place magnetic field uh, that is going via this, and then you have quantized magnetic flux in the structure over here. You can have also presence of Josephson junction here, but basically, let's say you have only electrodes. You put small voltage impulse between two electrodes that is going to lower that is going to lower the superconducting order parameter, and then if this is lowered enough, magnetic field is punched out of uh, the superconducting ring outside. So in a sense, this magnetic flux can move, is ejected. Will move outside, out of superconducting loop. And you can exercise this story if you have superconducting cable here, like two superconducting cables, and there will be some Josephson junctions in between, and they and uh, and then you can force this magnetic field to move from one cell to another cell with proper voltage impulses across here, or current impulses. You can also use current as modulating factor. So this is so-called Josephson junction transmission line. So your magnetic flux can move from one to another, from one to another. And then the presence of vortex, one quantized vortex, is uh, is means logical bit one, and its absence a logical zero. So so in a way, this is way to represent classical bits in classical superconducting electronics. So you can have transfer of information across the circuit. So you can shift this presence of this vortex. You can have a storage for a certain time. And then you can also execute operations on vortices. So you can have different type of logical gates, which I'm likely to describe in quite short time. So this process of transfer of vortices, this process of movement of vortices is very low, energy consuming. I'm sorry for a second. Okay, so what we have here, so we have a movement of vortices. And this just to let you know how this operation is power saving, I will mention that rapid single quantum flux electronics can carry out logical operations with power of 10 to the power 4 from 10,000 to 1 million of less energy consuming than in best current known semiconductor CMOS based electronics. So this is very effective. You can see very effective operations on superconducting circuits. So efficient from energy point of view. So basic version is rapid single quantum flux electronics. It was invented by Likarev, and then he was a Russian physicist that is already in Stony Brook. Actually, he's supposed to be one of the Nobel Prize winner, in my view, at least. And so he is right now in New York, but so he has created this rapid single quantum flux electronics. It was developed by Japanese, by Fujisawa and by Fujimaki and Yoshikawa, for example, and a bunch of other Japanese guys. And then was the invention of adiabatic quantum flux parametron logic that is even more energy saving. This is 1 million times less. In case of rapid single quantum flux electronics is 10,000 less than in CMOS, semiconductor CMOS. So this constitutes basically the operations on classical operations on superconducting circuits. All right. Then how to do logic? Well, I would say that you have A and B, and output is here. And so you can have XOR gate as given here. So you have also clock that is also with similar case as similar type of pattern, which is very characteristic for rapid single quantum flux electronics. So you can basically have the whole analogy of switching states, between classical states in a deterministic way with a CMOS technology. Actually, you can have very similar speed of the clock, and this is quite. So it is your speed of clock in superconducting electronics will be 100. Well, in range of 100 gigahertz, but the difference is with semiconductor technology. The difference is that there will be very low power dissipation. So one microprocessor, superconducting microprocessor can only, in a sense, waste 1 milliwatt of power. And but this has to be paid at the price of keeping it at low temperatures. And usually it's like 10 Kelvin in niobium or niobium nitrate. So we have this is very efficient representation of the circuits. And some people even expect that the rapid single quantum flux electronics can replace semiconductor mainframe computers. Well, I would say the only lack of random access memory is the problem, because we have all other circuits available and running. So with sufficient big size of superconducting classical computer, this is economic solution, because the price cooling is proportional to the surface, while the price of um, while the computation power is proportional to volume. So if you have sufficiently big ball, its volume will benefit computational benefit from volume that is very low power consumption will be enough to make such investment possible. There was idea of placement of superconducting classical computer on the moon, and there was a race between Soviet Union and the United States, and Likarev got a very big grant, but like more than $1 million US, which was a lot in Soviet Union time. But then the Soviet Union has collapsed, and he basically escaped Soviet Union since there was not stable economic situation. So anyway, this idea of placement of rapid single quantum flux electronics on the moon is vital idea and possible. And also, due to the temperature of space, this 10 millikelvin is a very good number. You don't need sometimes even use cooling device in space. Of course, you have other things like problems with radiation and things like that. Okay, so Japanese has also invested a lot in this type of technology. When I was leaving my first postdoc position, there was more than 100,000 Josephson junctions per chip. And well, I would say like some investments in classical supercomputers, there's requirement of usage 150 megawatts of power. That's a lot. That's absolutely a lot. And there's much less power consumption if you use, I don't know, a lot of superconducting microprocessors. So what I'm saying right now is currently saying classical supercomputers, superconducting computers are much better developed than quantum superconducting computers. But there is a path to interlink them both. Basically, you have integration processes as given here. So you have a lot of layers of superconductors. I will come to this aspect quite soon, to this technical issue quite soon. Okay, now let me refer to the block space. This is a qubit representation in block space. So we have 0 and 1. So essentially we have two real numbers, two angles that give position on block sphere in a unique way. So this is how it is. Okay, and now let me move to this existing architectures of qubits. One is Cooper pair box. Cooper pair box is a small superconducting island, small grain of superconductor that is separated with some insulator and later big superconducting material. And there's external electrode that controls occupation of this Cooper pairs in this small island. This is called Cooper pair box. And then you can regulate number of Cooper pairs in small area of superconductor. Then you have a next solution is phase. I would say it's magnetic flux qubit. So this is superconducting ring interrupted by one or more Josephson junctions. And then when you bias system externally, then you have you have presence of multiple fluxons inside the system. So you basically regulate. And so here it's what is pointed out is this washboard potential concept, which we have described some time ago. So then in this washboard potential, certain solutions are quantized, and then you can use these quantized levels for quantum information process. So this is magnetic flux box. And the first solution is phase superconducting qubit. In this phase superconducting qubit, you have Josephson junction and you have current source. So you force certain current to flow via Josephson junction. Then we already derived this case of washboard potential in the case of resistance going to infinity. And then there was this nonlinear potential and this nonlinear oscillator. We gave a prescription how to quantize this nonlinear oscillator. And then there's existence of certain quantized levels, energy levels. So there are three main architectures, but right now, in a sense, only two are used mostly. The first and the second intermix this. So this stands for transpond superconducting qubit. Okay, and from the point of view of logic, so before you remember, so here we create, so there's external solenoid that is usually also superconducting, so there is no heat flow. So so basically we regulate, so we think this, let's say this is D-Wave company concept to use this flux superconducting qubit on massive scale. And well, I would say you can think about usage of such superconducting qubit coupled to previously predefined. So let me move back. So this is coupled to this type of electronics, because here is also usage of flux. So you think that you can talk to your qubit with external flux moving nearby. That's a relatively good idea. Well, I will mention about that in greater detail. So yeah, so we have just for the purpose of your reference. So superconducting qubits are quite big. It's just to give you a rough estimation. So superconducting qubits are not challenging from lithography point of view. They are in size of 1 micrometers in total. Well, it is absolutely doable in Poland, for example. So you have this possibility of implementing them. And this is also important to recognize the Josephson junction as nonlinear inductance. That's one of this interpretation that can be grasped. I will move to that interpretation a little bit later. Yeah, so basically you have, technically speaking, nonlinear potential, which constitutes the washboard potential stands for nonlinear potential, nonlinear harmonic potential. So in ideal harmonic potential, you have equal distance between energy levels. And in case of anharmonic potential, this distance is not equal anymore. So basically, you cool down the system to 10, 20 millikelvin, and then you regulate the occupancy of levels. There are certain solutions of this washboard potential. The Schrödinger equation with washboard potential that can be achieved numeric. Okay, and now there's a lot of variants of superconducting qubits. Well, one of these variants stands for X1 circuit, but it's just variation of trans1 qubit in a way. So what is the idea? The idea is that you have two junctions in parallel, and you have you bias this by electric field, the occupancy of certain well. So this is nothing else than combination of this is combination of the first and second scheme. So this is the combination of both schemes. So okay, so we have so we are using both. So okay, so this is just to let you know. I will perhaps one day I will spend more time on trans1 qubit study in greater detail. And now, what is the concept of communication between Josephson junction qubit and between superconducting classical electronics as using this vortices of magnetic flux. So vortices of magnetic flux are traveling via Josephson transmission line, as I mentioned at the very beginning. And then, of course, then you can have a qubit, like flux qubit, superconducting ring interrupted by free Josephson junction. That's given here. And of course, they will talk. You can have also external solenoid from here. So this traveling fluxon can imprint certain physical state on the qubit, or it can pick up certain state of the qubit. So this is the way of interaction. But there is you need to of course write down the Hamiltonians and solve them and prepare the structures and so on and so on. The problem is that usually this rapid single quantum flux electronics can work, let's say at 10, depends on the material, in NBN and B, like niobium, 10 Kelvin, let's say. Then it is relatively high temperature, but it can also work at lower temperatures. There's no problem with that. The problem is that with writing of superconducting qubit by means of classical information representation by vortex, it always leads to heating up of the qubit. So what I'm saying is that this communication process is going to heat up the qubit, so it cannot be done too often. But imagine you can have certain quantum logic implemented on the chain of superconducting qubits on the top, and you have a massive classical logical circuit underneath that, for example, implements your spiking neural network, classical spiking neural network. So you can do both, but you need to design the algorithms and the procedure of communication in such a way that it does not bring to too often communication. So in a sense that you need, because once the qubit is heated up, it needs some time to rest, to go to the ground state. So this is a certain process which takes time. So you have to be able to design algorithms for algorithms for classical quantum algorithms that are using massively classical uh, parts and not so often quantum parts, because quantum part is always very expensive. So just I want to bring your awareness of that. But basically, there's the whole system can be placed in 10, 20 millikelvin. This was already exercised by various groups worldwide, by the way. So now there is a chance to update this Wrocław project. So in a sense, to add this interface and then to go for more commercial classical quantum computer. Then this is just the case of small superconducting qubit system. All right, and there is a bunch family of products by D-Wave company. That was a quite first big quantum company. They massively produce flux superconducting qubits, and then they argue that they get a certain information processing speed up due to tunneling between barriers. So in a sense that due to this process of tunneling, there is such a process known as annealing in classical information processing, but you can speed it up by local quantum tunneling. So that's one of the feature of speed up in case of D-Wave company products. So this is somehow interesting. By the way, we can also think about superconducting computers, classical computer, and interfacing qubit. And this qubit can be also sensor. This is also very important. This could be also sensor. It doesn't have to be just superconducting quantum computer. It can be also sensor. And this is how this equipment looks like. Is by no chance easy task. It's technically quite hard. You have the whole system controlling qubit setting and readout. Usually it's done by microwaves and waveguides, and everything is placed in dilution refrigerator at the bottom. So basically you send impulses, microwave impulses in the range of gigahertz frequency, and then you set up or read out the state by such type of impulses. The problem with current state of superconducting technology is that the waveguides take a lot of space. So there are different measures to. So this means that currently existing superconducting computers are not so much scalable. So due to this fact, they are not so much scalable. Well, this roadmap of many companies for 1 million qubits is a little bit of questionable in that sense, because it requires a lot of effort. And this is not necessarily, well, right now the number of IBM quantum experience qubits in IBM quantum experience can go beyond 500. But the more qubits, the less interconnected they are. That's naturally such type of it's natural that it's hard to make them all interconnected. And then you have various layers of temperature. You have 20 millikelvin over here, then you have 4 Kelvin, then 77 and 300. And then you have the different types of equipment. You can also, that's the whole family of classical electronics that can be constructed. You can construct amplifiers based on the Josephson junctions. They have very low noise. So you can amplify certain small signals with Josephson junctions. That's the whole art of doing so. Well, this art is not yet too much pronounced in Poland, unfortunately. So there is always a space to do something with that. Then just to give you a brief view, this is the case of quantum annealing chip by D-Wave company. It was one of the first big quantum companies created some time ago. Actually, partly basing from patents obtained from Professor Hannes Telfer students from Germany. They graduated, become a professor. So in a sense, a lot of technology was bought in Germany. So basically, you have niobium elements and SiO2, just like substance for isolator. So you are implementing, let's say, network of two-dimensional. You basically do two-dimensional lattice of superconducting cables, and then you can have movement of vortices across that. And this is pretty much the way you can conduct the operations. So basically what you have here is superconducting loops, and there are Josephson junctions here present. And then you can entangle two qubits with proper current delivered via time. And then you can get you can entangle various parts of this qubits. So basically it's shown how very different qubits can be entangled here. Okay, so basically this system of loops, of superconducting loops that are interacting, that's what I'm talking right now, can be Ising model, can express Ising model. So somehow they could be parameterized by that. And this Ising model could be derived from essentially from Bogov-Dijon equations or from Ginzburg-Landau equations. But I rather stress out that one's supposed to go rather into Bogov-Dijon equations dynamics. Just to give you this spiking neural networks in superconductors, why this is so much important. So there was some attempt to reproduce mouse brain, and we've currently you can use non-superconducting electronics for spiking neural networks, or you can use superconductors. And then there's a big difference of power consumption. So basically, what I'm trying to say is not efficient to have it's not efficient to have electronics at room temperature controlling superconducting qubits. It's better to have all superconducting. It's the first thing. So to have all things in the same cryogenic environment, in the same temperature, let's say almost the same or kind of nearly the same. So there are two attempts right now for a qubit development. One is referring to that you have CMOS, cryogenic CMOS technology. It's also at low temperatures that is nearby of Josephson junctions and takes part in its control. This is like Charbonnet, Eduardo Charbonnet, directional way of thinking from Switzerland. Another way of thinking is to have this interface to have this classical and quantum superconducting electronics in the same place. This is something which I'm kind of advocating, and this is remarkable to recognize that it doesn't require too good lithography. Okay, you can also exercise different type of Josephson junctions. This was some sort of, by my interest, like superconducting cable and ferromagnetic strip on the top. All right, so this is main part, let's say, of my presentation.